All right, so the p-series test is just an extension of our integral test, and what it does is it says that if we have a series with 1 over n to the p, that this is convergent, the series is convergent as long as p is greater than 1. Otherwise, it's going to be divergent if p is less than or equal to 1. So if you remember that from the video in 7.8d, it will explain why the integrals, the improper integrals, are convergent if p is greater than 1 and divergent if p is less than 1. It had to do with the integral ending up as a fraction. And so we need our p to be bigger than 1 so that after we take the integral, we end up with a rational expression that will then go to 0 when we take the limit. So all we have to do here is go, okay, well, n, which is equal to, or sorry, not n, p equals 3 here, which is greater than 1. So this is convergent. And you can see that here. There's my p of 3, and you can see we're underneath here. And so as I go off to infinity, you can see my integral is converging. And so all we're really doing is going back to our improper integrals. We already know that this is a continuous, positive, decreasing function. And so we're using the integral test. That's all we're doing. And we're then applying our p greater than 1 to make it a p-series test. So here we have to actually rewrite it. So this would be the sum from n equals 1 to infinity of 1 over n to the half. Well, our p here equals a half, which is less than or equal to 1. It's actually just less than, but I want to put the equal on there, which means divergent. Well, what if you have this? Well, we can combine them just like we've done before in these other problems. So this is n to the half right up here. And so we wrote 1, n, and then that would be 3 halves. So our p here is 3 halves. So all I'm doing is subtracting, and you want to subtract top from bottom, like that. And so that would give us 3 halves. And so that's your p. So all you're doing is to take away half. P is 3 halves, which is greater than 1. This is convergent. And that's it. It's that quick and that nice. So as p is greater than 1, when you take the integral, you're going to end up with a fraction, just like we did in 11.3a. So you can see we have an x to the negative 2 here. So at the very end, we're going to get a negative 1. So as long as this right here is bigger than 1, once we add that positive 1, this is going to remain negative, that exponent, leaving us with a rational expression, which will go off to 0, allowing it to converge. And so watching 7.8d, I do a lot of examples in there, and you can see exactly why. Well, how about this one? Well, if you remember our series, if they both converge, then the series converges. So what we can do is split it up. And what I want to do is rewrite that because I know I'm going to be subtracting it. So I'm going to rewrite it as an exponent. And so we have this. And then we can take and split our sums. Because remember, you're just adding these, so why not just add them? And then this would become the sum. I think you're already figuring out, oh, you can just do that. Yeah, that's all we're doing. And that's 3 halves, just like we did up there. And so here, our p equals 3 halves, which is greater than 1. Our p equals 2, which is greater than 1. And so if they both converge, then the series itself converges. So it is convergent. And that's your p-series test. So all you have to do is notice that our function matches with the integral test, right? And that's going to match. So if it's 1 over n to the p, as p is greater than 1, it converges. P is less than 1, it diverges. And if p equals 1, it also diverges. So watch 7.8d to figure out why.